Here we go. Hello, everybody. It's great to see so many people here. Actually, it's exciting. So let me start by introducing myself. I'm Christiane Rütten, and well, to my background, I mean, I started computer quite early, and I was administrator at Institute for Development and Peace, and that's where I learned the Linux basics. And well, lately I switched over to HISA security, maybe you know about it, and that's what I do for a living right now. I'm writing. And well, okay, let me first tell you about this lecture here, because this whole speak has been done for the Informatica Feminale. It's it's a place where a lot of women meet to take some IT courses and to chat. And this course essentially was held this year, and it took about 2 days. It was more kind of like a workshop, and everybody could ask me the questions, which was, in the case something wasn't too clear. And of course, all this isn't possible today. So we will have to see what's going on the slides, and I hope there won't be too many questions, because I had 6 hours for this talk, and well, actually now we have 1. So it's going to be a bit tense. So I hope I won't be expecting too much of you. It will be quite quick, I think, and you will have to pay a lot of attention, I think. And what I expect of you is, well, a good knowledge in a programming language. And you should really know what's going on there. I mean, you should know what is a variable, and maybe you should have heard about the stack and how that thing works and the abstract data types. And you should have profound knowledge maybe in a language like C or Java. And well, maybe you've even seen some assembler or something like that. And that will very much help you. I mean, I won't start by telling about variables and so on, and I will just think you are going to know it, and you should have an idea about how the computer inside works and the bus system and so on. And I'm going to make a very simple model of all this, because you don't have to go too deep into the matter to understand what's going on there. So, well, what all this here is about is buffer overflow exploitation. And I'm going to present it in a nutshell, and that will be a quite simple view on that, so that we can go through it within 1 hour. We'll start with an introduction to machine language, and I will show you some assembler output, and I will show you some, well, instructions, and we'll see about that. I will show you a simple memory model, which is very much the model that is used by Linux. And this is going to be the platform we are looking at. It's Intel 386 on a Linux platform, because this platform is a very simple platform to understand, and the principles are all the same. It would be a hell of a lot more different and more difficult on a Windows platform, so we're going to do Intel on Linux. Well, then we will see how functions in C are called, because that's where the problem arises. It's actually the buffer overflow problems is a problem of the language you're using, and actually it's a compiler. And so, because most of modern programs and modern operating systems are written in C, this is a problem that you will find quite everywhere. But we are going to concentrate on the GNU C compiler collection, and because it's available everywhere, and I think most of you will be able to go through this at home or something like that. Okay, then we will see what is a buffer overflow, how does it happen, and where actually is that buffer, and what is it we're talking about here. And then we will see how all this can be exploited to let programs do what we want them to do and what they were not designed to do. And therefore, we just need to know what is the shell code because how can we go on and write a shell code? And I will show you about that. You will see a lot of debugger outputs, and I think it will help you understand what's going on there. And if you've got enough time for that, there will be some countermeasures and what you can do against it. And well, so let's start with the introduction to machine language. And I will tell you about the central processing unit. I mean, most of you will probably have heard it through IT courses anywhere. It's just a very basic and simplified model I'm going to tell. And we will see that the important part will be the registers to understand what's going on into the machine language. And we will go through some example instructions, and there will be a quick note on the endianness, or, well, it's otherwise called byte order. So that's a pretty simple CPU model. And you can see there's a CPU that's attached to a bus, and the bus itself is attached to the main memory, and the CPU is going to fetch instructions over the bus. And there's one thing to say about that, because instructions or data, I mean, you cannot really tell. And it's a question of interpretation. And that's going to be a key point to understanding what buffer overflowing is about, because things that should be data are going to be interpreted as instructions. And that's how all the thing is going to work. What a CPU does is nothing more than some flow control. I mean, like jumps and branches to other points. And it does, of course, arithmetic operations on the registers. And if it's not a load store architecture, it can even do these operations on memory directly. And of course, the CPU loads and stores data from into memory. There's nothing more to it. Well, but actually, of course, you know, this is pretty simple. I didn't tell you the whole truth. If you look at this, I mean, in reality, it's quite a bit more complicated, and that's the PDP-11 from 1971. You don't need to know all about that, but that's a more realistic CPU model. And actually, that's a CPU model from a PDA of LSI, and you can see there's a lot going on. The memory is much more segmented, and you've got pipelines, and you've got execution units, and I didn't tell you about the cache, and I didn't tell you about lots of things, but you really don't know about that. So GMA, I just let everything out. Forget about that. There's one thing about the CPU that's very important, and that's the registers. Now, the registers are little memory units within the CPU that can be operated on and that have a special function. And in this very special case, the i386, which of course is all the Pentium and the Athlon and all the other more modern processors from Intel are quite backwards compatible. So we will just fix on that one, because that will be sufficient to understand what's going on. So we've got 8 general purpose registers, which are 32-bit wide. And 4 of these are just arithmetic registers. They are called EAX, EBX, and ECX, and EDX. And they basically are used for arithmetic operations. You will see what's going on there later. And actually, there's one thing about these registers. I mean, they look quite complicated. Why didn't they just call them A, B, C, and D or something like that? That's because they were extended. All this started, well, when Intel just brought out the first processors, like the 8080. And you can still address those 32-bit wide registers in bits and pieces. So you can just address the lower 8 bits, the lower byte, by just addressing AL. And you can address the lower word with AX. And maybe you are going to, you're probably not going to need this, because most operating systems are working in 32-bit only. Okay, what we else have for address registers, they're used, well, as the name suggests, they're used for for addresses, and the most important ones will be the stack pointer and the base pointer. And we're going to see how they are being used. And there's one very important register, which actually is a kind of read-only address register. That's the instruction pointer. That's just a pointer where the execution flow is at right now. That means it points to the instruction that it's going to be executed at next. Well, okay, there are even more registers, but the 6 segmented registers, they're unused today because we have a flat memory model, and this is just, well, historic, for historic reasons. And the flags register, that's a register where some bits are set when maybe, for example, the last operation had yielded 0, and so that can be checked by the following operation. That's flags, and it just represents the status of the CPU. So let's go through some examples of the i386. And one of the most important ones, you won't believe it, is the knob. It's no operation, it's just do nothing. And we've got the move operations, like the second one here. It's going to store the value 17. It's hexadecimal. I mean, I guess I just suppose you know how you calculate that. It's the decimal value of 17, and it's going to be stored in the register EAX. Well, the next one would be, this is an addition, and the B that you can see right here, it just indicates that we have got a byte value. It could be a W if you are using a word, I mean 16 bits, or it could be a L if we are using long words, that would be 32 bits. But in this case, it's not clear if we're putting a byte, a word, or a long word. So we just designate with a B. So it's clear that we have an 8-bit value that is stored into memory. And there's one, this is a peculiar one. This one is called indirect addressing. And in this case, if the register is in brackets, it's not stored in the register itself, but it's stored into the memory address that is pointed to by the register. So actually, if you see that notation, it's just a pointer. So there are more operations that are quite important. Let's look at the push operation. I mean, it's that what you know when you're working with stack. The push operation just puts value onto the stack. In this case, it's the value of the base pointer that is saved onto the stack. And actually, if you go through this, you will see that the push is constituted of 2 sub-steps. The first one is to decrease the stack pointer by 4 bytes, which is just the width of the value we are storing here. And the next step would be to store the value of the base pointer to the address where the stack pointer just points to. We will see how that's going on in another slide. I mean, I will go into some detail there because this is quite important to understand what's going on there. The reverse operation of push, of course, is pop, and it just does the reverse. It fetches the value from the stack and stores it into the register that is given here. So this is just the other way around as designated above. This is just take the value from the pointer in ESP and store it into the base pointer and add 4 to the stack pointer. Some more examples would be the jump. It's just continue at the address given under any circumstance.